All right, so equations of circles. The standard form for the equation of a circle is this: x minus h squared plus, always a plus sign, y minus k squared is equal to r squared. A circle, by definition, is a group of points that are equidistant from one central point. That center in the equation is at HK. Okay, it's going to be in those parentheses with the X and the Y. Okay. The radius, that equal distance that those points are from the center point, is R. Notice this is R squared in the problem. They're not usually going to write it like if the radius is 3, they're not going to write 3 squared over there. They're going to write 9. So we've got to kind of decode a little bit of stuff here to get things going on that. So X variable is always there. Y variable that's always there. H, K, and R are going to be numbers. So as we decode this stuff, that's what we're looking for. Okay, so first game we'll play is state the center and the radius of the circle, and we're going to be given the equation. Let's say x minus 5 squared plus y minus 3 squared is equal to 16. So using our decoder ring there, with the x minus h squared plus y minus k squared equals r squared, we know that the center is at the ordered pair 5, 3. That's coming from those. So the opposite of whatever's in the parentheses there, it's a minus 5, it's going to be positive 5. It's a minus 3, it's going to be positive 3. If it were pluses, it'd be negatives. The radius, we're going to take the square root of whatever number the whole thing is equal to. Equal to 16. So what's the square root of 16? 4. So the radius is 4. And we'll always use just the principal square root or the positive side of the square root because radius is a distance. So it's always going to be positive. So don't worry about the plus or minus, when we do square roots. Solving quadratics, we always did the plus or minus. Don't worry about that with circles. We're just trying to get that whatever the radius is, and the positive side's all we need. X plus 3 squared plus y minus 4 squared equals 36. Same game. State the center and the radius. What's the center of this one? Negative 3, 4. That's correct. The radius, 6, coming from the square root of 36. There's the center, there's the radius. Let's do another. Throw a curveball at you here. It's a little different, change of speed. But if you ever played baseball, this is what you call the hanger. It's just sitting there spinning, waiting for you to hit it. There's no parentheses on the x. So what's the x value of the center? 0. There's nothing there, so it's 0. And then the y value, negative 7. Opposite of plus 7 is negative 7. The radius, square root of 12 reduces to be 2 radical 3. If we needed a decimal approximation for that, it'd be somewhere around 3.46. No, I don't do that in my head. I just have it memorized. That's one that comes up quite often. So, but if you needed a decimal approximation, most of the time, the 2 radical 3 is what you want to get for a solution. But there may be times that you might need a decimal approximation. So you just take the square root of 12. It's about 3.46. That's a pretty easy thing. All right. Let's go in the synthesis side of things. So they're taking it the other direction. Given a center and a radius, write the equation. Okay, so simple D, write the equation for a circle with center at 6, 8 and a radius of 7. Plug in the stuff we know, or that should be a Y there. There you go. What goes in the first parentheses? -6. Second one, -8. Over here on the other end, 49, because that's what 7 squared is. And there's the equation of a circle with that center and that given radius. Okay. Easy enough. Let's say it's a center at -13, 0 with radius square root of 8. What's our equation? Doesn't get much more difficult than that, guys. It really is straightforward. That's what we want to do with circles in this particular course. And there's nothing that comes up in 110 that really relates back to having to do anything else with it. Just kind of grabbing that equation for a circle, given a center and a radius, or writing the equation given the center and the radius to get that stuff. Great. All right, so that gets us the unrelated section for the night. Let's go ahead and jump into the two related sections. The first one, we're going into R3. We've hit R3, I don't know how many times this semester. I think this is the last time we'll go to R3 this semester. It's long division. We've kind of got pieces of R3 throughout, and this is the last piece that we need from it for 100. Polynomial long division. So long division, everybody's favorite thing from 3rd grade. My wife says I'm a weird person because I used to sit there. I thought long division was cool, and I would sit there and do long division for fun. And it worked out well for me because I ended up being a math teacher. But most people don't do that. But long division, if you're taking, just do some numbers just to get back to thinking about how to do long division from when we were kids. Let's say we took 13 into 285. Okay. With long division, so doing it without a calculator, and done that in quite a while probably. So we look at that and we say, okay, how many times does 13 go into 2? Won't go at all, right? So we go to the next digit. How many times does 13 go into 28? Twice. And then what do we do next? Yeah, we multiply whatever we put up top times the stuff that's in front. So it's a 13 in front, so 2 times 13 is 26, and then we subtract that. And we get 2, and then we bring down the 5. And then we look at that and say, okay, it's 25 now. How many times does 13 go into 25? 1 time. Then what do we do with that 1? We multiply it to the stuff in front and get 13, and then we subtract again. And we get 12 this time. Is this smaller than what we divided by? Yes. So that's our remainder. Okay. And we used to write it like this. I remember doing that. Or seeing something like that. That's how we did it in elementary school. And then we got to high school or this class and we threw a calculator at you and said do it with a calculator and don't worry about that. But here's the idea. That style of long division works well with polynomials too. Okay, so let's look at a polynomial problem. And you may not catch it on the first example. Don't get frustrated. We're going to get there. We're going to take a polynomial, x to the third plus 6x squared minus 8x plus 10. And we're going to divide it by, we'll start with a really small polynomial to divide by, x plus 3. So I'm going to set up a long division problem. Give myself plenty of room here. What's on top goes inside. So when you're putting this down, when you're writing down for long division, you need to make sure that it's in descending order and that you've got a representative from each power, starting with the biggest one. So here we have x cubed, then there's an x squared, then there's an x, and then there's something that doesn't have x's. There is a representative for each one, starting with the biggest one. If there's not one, we need to put one in its place. We'd put a 0 x squared if there was no x squared. We'll see an example of that in a little bit. But you've got to make sure you got a representative from each one. So I got x cubed plus 6x squared minus 8x plus 10. On the outside, same rule. Descending order and a representative from the highest power of what you're dividing by, your divisor. Okay. X and 3, x is the highest power. So that's x to the first, then there's no x's. So everybody's there. If there was somebody missing, you put a 0, whatever was missing, in its place. If you do that, it makes things work more, I won't say easier, but it just keeps it organized more easily. It's more easily organized as long as you've got a representative from each one. All right, now, here's the trick to doing long division with polynomials. Don't worry about the plus 3. Only worry about the x in the front. The plus 3 is, as I say in military bombings, collateral damage. Okay, it just happens. Okay, whatever happens with the 3, just part of the game. Okay, so x, what times x would get me x to the third? X squared. I'm going to put the x squared right there because that's what would get me x cubed. But that x squared is it's kind of like they've got columns for each piece. Okay. Now, just like up here when we did the number, we multiplied 2 times 20 times 13 got 26. We're going to do the same thing with this x squared. We're going to say x squared times x. That's x cubed. And then we got to say x squared times 3. That's 3x squared. And so it's like distributive property there. It's not like it. It is distributive property. X squared times everything that's out in front. Then this is very important. Put it in parentheses with a minus sign out in front. That's going to remind you that you're subtracting that entire piece, not just one of the pieces. So I always put that in parentheses with a minus sign out front. Then what happens when you subtract x cubed minus x cubed? They get 0. They cancel out, right? Then we're going to say 6x squared minus 3x squared. It's 3x squared. Then we bring down the minus 8x. Just like we brought down the 5 when we did the example with the number. Okay. Now we look at this step and say, okay, what times x gets me 3x squared? So I need a 3. And I've got one x out here. I need one more, right? So 3x times x gives me 3x squared. That's what I need. So I'm going to use the 3x squared. Or 3x, sorry, to get 3x squared. Distribute. Parentheses, subtract. 3x times x is 3x squared. This times this gives me that. 3x times 3 gets me the 9x. That's where that's coming from. I'm distributing the 3x to both terms. Then I subtract. What happens to the 3x squareds? They cancel out. That's what I want to happen. That should happen every time. If that doesn't happen, then you got the wrong number up there. Okay. Then you do the subtraction. What's negative 8 minus 9? Negative 17x. And then what do you do with that 10? Bring it down. Then we look at the 17x. What times x would get me negative 17x? Negative 17. Distribute. Negative 17 times x, negative 17x. Negative 17 times 3, negative 51. Parentheses, subtract. 17x's cancel, just like they should. Then we got 10 minus negative 51. That's 61. That guy right there is our remainder. Okay. The reason we know that's the remainder is because there's nothing I can multiply this x by and get a plain 61, right? Because anything I multiply times an x is going to get me something with an x on it. So that makes this polynomial-wise smaller than the divisor. Like up above we had 12 was the remainder. It was smaller than what we divided by because there was nothing we could multiply 13 by and make it smaller, like not a nice number. Okay, so this is my remainder. Okay, so we can write our answer x squared plus 3x minus 17. That's what all the stuff we wrote up top. That's what that is. Plus the remainder over what we divided by. And that would be your answer to that problem. Okay. Got to follow that process pretty much every time to do long division with polynomials. Let's look at another one. Let's say we had 4m to the third minus 8m squared plus 5m plus 6 divided by 2m minus 1. So we're going to set that up in synthetic division, in long division, not synthetic yet. 4m to the third minus 8m squared plus 5m plus 6. We start with m to the third. There is an m squared. There is an m. Then nothing. No m. Okay, so we've got a representative from everyone. Again, if there's one missing, you got to put a 0, whatever's missing. Okay. Then on the bottom, what we're dividing by, the divisor, 2m minus 1, that works. Got m and then no m's. So that's in descending order. There's nothing missing. Then I look at the front pieces, 2m and 4m cubed. What times 2m gets me 4m cubed? 2m squared. Then what do I do with this 2m squared that's up here? Multiply it to the stuff that's in front. So that's 4m to the third minus 2m squared. Parentheses, subtract. What happens to the 4m cubes? They cancel out. That should happen every time. If it doesn't, something's not going right. And then you do the subtraction. Negative 8m squared minus negative 2m squared. Minus a negative is like plus, so negative 8 plus 2, negative 6m squared. Bring down the next piece. If you want to do arrows to help you stay organized, you can. What times 2m gets me negative 6m squared? Negative 3m. Minus 3. Distribute the negative 3m. That's negative 6m squared. And negative, or positive, excuse me, I made a mistake there. Negative 3m times negative 1 is positive 3m. And then parentheses and subtract. The m squareds cancel, just like we wanted them to. 5m minus 3m. Two m, right? Bring down the plus 6. Is there anything times 2m that gets me 2m? 1 plus 1. Distribute. It's always easy to multiply by 1. And then subtract. 2m's cancel. 6 minus negative 1 is 7. We know that's our remainder. So our quotient will be 2m squared minus 3m plus 1 plus 7 over 2m minus 1. It's a very methodical process for long division. Synthetic division is too, but long division, a lot more stuff going on with long division. You got all those letters involved. Makes it kind of tough to do. Let's do one more here. Let's do 3x to the third minus 2x squared minus 150 divided by x squared minus 4. So there's our original problem. Let's put it in the long division machine. It goes on the inside. Three x cubed minus 2x squared. And then we need a 0x because there's not a plain x. Remember, we got to have a representative starting with the highest power. We got a cubed. We got a squared. We don't have a plain x. So we're going to put plus 0x and then minus 150. What goes on the outside? Well, we got a missing piece out there too. Plus 0x minus 4. If you leave out that missing piece, you'll what I've always seen happen over the last several years of teaching the higher level maths in high school and then these classes here is that if folks that leave out those missing pieces quickly get confused because stuff doesn't line up. But if you put those missing pieces in it, you could follow the process really easily because stuff lines up perfectly. So those missing pieces are important. Those 0 x's and 0, or 0 whatever's missing are very important because it makes things line up the right way. Okay. Now we look at the front. What times x squared gets me 3x cubed? 3x. So I need a 3x. So I put that over the x column. And then I distribute 3x times x squared is 3x cubed. 3x times 0x, that's easy, it's 0x squared. 3x times negative 4, negative 12x. Parentheses. X cubes cancel. Negative 2x minus, or negative 2x squared minus 0x squared. Negative 2x squared. 0x squared minus negative 12x. Yeah, it makes it a positive 12x. Good. Bring down the next piece. What times x squared gets me negative 2x squared? Negative 2. And then subtract. We know this is the remainder. Here, 12x is smaller than x squared because x squared obviously is bigger than the plain x. So that's how we know we're done. And so we write our solution or our quotient and remainder 3x minus 2 plus 12x minus 158 over, and we can go back to x squared minus 4 there, just to shorten it up a little bit. We've done long division. That long division is really about the only time you use it is if you're having to divide by something that is a higher power of x, like x squared minus 4 or x cubed or something like that. Anytime you're having to divide by a larger power other than plain x or plain m or whatever variable you're dealing with, long division is used for that. Synthetic division, which we're about to go over, is used for linear factors, things you're trying to divide that are linear, meaning they have the highest power of x to the first. Okay, and so long division, it's one of those things that's going to come back up in 110 because we do some stuff with rational functions, and you've got to do some long division there to get some of the things built in there. But synthetic division is a very useful tool in polynomials, which is what we're kind of going to use it for in Math 100. We'll use it some in Math 110 as well. So let's look at synthetic division and see what we can do with it. So synthetic division, as I said, can be used with linear divisors. Linear divisors. That means things like x minus 5, 3x plus 7, 2m minus 1. Those are linear divisors because they don't have an exponent on the variable that's bigger than 1. Those are linear divisors. If you're dividing by anything bigger than linear, then you have to use long division. You can't use synthetic. Synthetic means it's a shortcut method, which means it only works for certain things. It's kind of like the FOIL method for multiplying out binomial times binomial. It only works for binomial times binomial. It's not a tool that works for everything like distributed property is. Synthetic division only works with linear pieces. So polynomial long division works for everything. We did some examples of dividing by linear divisors with long division. Synthetic division makes it better. Okay, I'm going to show you that as we go through this. Okay, so synthetic division, same idea. You got the problem set up the same way. You got 5x to the third minus 6x squared minus 28x minus 2. And then you're dividing that by a linear divisor. In this case, x plus 2. Okay. When you're doing synthetic division, you want to set up a box with a little shelf there. You need 2 lines inside that box. So that's why I drew it on 2 pieces, 2 lines of my notebook paper there. Okay. The top row is the coefficients of your dividend, what you're dividing into. So 5, negative 6, negative 28, negative 2. Same rule applies for this as it did for long division. If you got a missing piece, you got to put a 0 in its place. Okay. There are no missing pieces in this one. So we're going to put 5, negative 6, negative 28, and negative 2. We don't bring the variables with us. Leave those out. That's the nice part about synthetic division. You don't have to deal with all those variables. You don't have to deal with the distributive property either. Okay. Now, that little shelf out there on the side, we got to get a number on there. To get that number, you take your divisor and you set the divisor equal to 0 and solve. So our divisor is x plus 2. So we're setting x plus 2 equals 0 and solving that. X equals negative 2. That is what goes on the shelf. That's what's my term. That's a highly technical term, on the shelf. That's our synthetic divisor is what that's actually called. So the synthetic divisor. But this number that goes on the shelf. So we're going to put negative 2 up here. Now, the way synthetic division works, in long division, we use subtraction every time. Synthetic division uses addition, which makes it even better. Addition is much easier than subtraction, right? Especially if you got 2 negatives, because you got a bunch of negatives going on and a subtraction sign, it can make it very difficult. Synthetic division is great because it only uses addition. So to get the ball rolling, you drop the first term down. So 5 drops down. Every time with synthetic division, you're going to do that. You drop that first one down. Then you multiply. 5 times negative 2, negative 10. And add. Negative 6 plus negative 10, negative 16. Multiply. Negative 16 times negative 2, 32, positive. And then add. Negative 28 plus 32, 4. Multiply. 4 times negative 2, negative 8. Negative 2 plus negative 8, negative 10. This last number here, that right there, is your remainder. So our I can do minus 16x plus 4 plus negative 10 over x plus 2. Synthetic division always takes your degree of your polynomial. This one started with 5x to the third. Anytime you do synthetic division, one time down breaks it down by 1. So we go from 5x cubed to our quotient being 5x squared. It always takes it down 1. Synthetic division always takes it down 1. Because you think about it, you're dividing an x cubed by plain x. X cubed divided by x is x squared. So that's why we're ended up here. We got 5x squared minus 16x plus 4 plus remainder over what we divided by, just like we did in long division. Okay. There's also another way to write the solution to this, and that would be writing it as x plus 2 times 5x squared minus 16x plus 4, and then minus 10. That's also an accepted format. Know both of them. This is correct. This is also correct. So this one, you got what you divided by out in front times this stuff, and then close the parentheses, and your remainder's hanging out here on the end. It just puts things in a different spot. It means the same thing. These two things are synonymous. They mean the same thing. Okay. Sometimes they're going to ask you for it in different forms. So I want to make sure we cover that. All right, let's do another synthetic division. Say that again. You got to know which one. When can you do synthetic division? You can do synthetic. We'll get to one where I'll show you. Like this is normally the f of x equals is normally when you're given a polynomial and they're saying, is this a factor of it? And I'll show you that in just a little bit. Let's get the process of synthetic division, and then we'll get there. Good question. Yeah. When will you know which one to do? Usually, it's when you've got an f of x given to you, like you've got a function given to you to start off with, instead of just a division problem. The top way is usually when you're just given a division problem like this: negative x to the fourth plus 3x squared minus 4x minus 5 divided by x plus 3. Usually when you're given it like this, you'll do the form where you got the fraction on the end. That's normally how you'll do these. So let's set this up for synthetic. What goes on the top row? Negative 1. Why did I leave space there? Yeah, I don't have an x to the third there, so I got to put a 0 in its place. Got to have a representative from every power, starting with the biggest. We had x to the fourth to start off with, so we need an x to the fourth, x to the third, squared, plain, and then no variable. What goes on the shelf? Negative 3. How'd you get that? Yeah, x plus 3 equals 0. Solve it. You get negative 3. So that's what goes on the shelf. How do we get the ball rolling? Drop that negative 1 down. Then what? Multiply. Negative 1 times negative 3. 3. And add. Multiply. Add. Multiply. Add. Multiply. 3 times 14. 42. Negative. Remainder. Negative 47. I usually just box in that remainder because it helps me kind of keep it organized. I always box in that remainder there. Okay. So this was in the division problem format, so we could write this in that fraction format. So we started with x to the fourth. That means our quotient starts with what? X to the third. So negative 1 x to the third plus 3x squared minus 6x plus 14 plus negative 47 over x plus 3. So will the first x always be less than what you started with. Yes, absolutely. Yeah, always. Anytime you use synthetic division, it will always be that. Which, next week we'll talk about how this relates to taking a polynomial and breaking it down. All right, so let's look at the remainder and factor theorem and how it relates to this. What the remainder and factor theorem says is if the remainder is 0, then the divisor is a factor of the polynomial. It also indirectly states that the value is also a 0 or x-intercept of the polynomial. Which will kind of lead us. That's what we will use. We will hinge on that statement next week. That's what we're doing. Okay. All right. So this is what we're going to do. We're going to determine if k is a 0 of f of x so as Ms. Luanda asked about when do we write our answer in that certain form, this is one of those cases where if they ask for us to write it in factored form or something like that, that's that form we're going for. So here's our polynomial, x to the third minus 4x squared plus 9x minus 6. And k is equal to positive 1. Now, when we're setting this up, the difference here is that they're not asking us to divide by certain linear piece. They're asking us to decide if 1 is a 0 of this. What we can do is use that in synthetic division to decide if it's a 0. And the rule is if the remainder is 0, then that number is a 0 or an x-intercept. Okay? So we're going to set up synthetic division the same way. And we're going to, instead of changing the sign, because this is not a factor, we're just going to keep it a 1 there on the shelf. Positive 1. Here's a hint. This actually came from x minus 1. That's where that's coming from. K equals 1 really is x minus 1 as a factor. Like that's relating it back to the last two examples we did. It's like dividing by x minus 1. Okay. Now run synthetic division with that. So drop the 1 down, multiply, add. And we get a remainder of 0. What that means k equals 1 is a 0 of f of x. It also means that x equals 1 is an x-intercept of f of x. It also means that x minus 1 is a factor of f of x. All of that from the 0 being in the remainder. Very, very powerful theorem. for this. That if we can get a 0 in the remainder, then it does all of these things. It means that the number we divided by is a 0 for the polynomial. It means that that number is also an x-intercept. Zeros and x-intercepts are the same thing. Okay? And then x minus 1 is a factor of that polynomial. Okay, so that's what that means. So this could be a simple yes/no question that they ask: is k a 0 of the polynomial? You do synthetic division. If you get a 0 as the remainder, the answer is yes. They could be asking us to write this in that factored form because we got a function notation that f of x equals. If they did, we'd be dividing by x minus 1. Here's what's left. X squared minus 3x plus 6. Our remainder is 0. That's what's going there. So technically, you wouldn't have to write the plus 0. I'm writing it there because it doesn't change anything. It tells us a whole lot. X minus 1 came from the k equals 1. And then the x squared minus 3x plus 6 is the quotient from the synthetic division. We started with x cubed. It goes down 1. So that's why we start with x squared minus 3x plus 6 out of that. Okay. All right, let's look at another one. Here's our function. F of x is equal to x to the 4th power minus 2x cubed plus 4x squared plus 2x minus 5. And we want to decide about k equals negative 4. Is that a 0 of that polynomial? So I'm going to set up synthetic. 1, negative 2, 4, 2, negative 5, negative 4 on the shelf. I didn't have to put any zeros in there because I didn't have any missing pieces. The negative 4 is what they asked me to test, so that's what goes on the shelf. Then get the ball rolling with synthetic division. Drop the 1 down. Multiply. Add. Multiply. Add. Multiply. It's a big number, right? Negative 112. And do that addition pretty easily. That number's a little easier, positive 440. My remainder, 435. Is negative 4 a 0 to that polynomial? No, negative 4 is not a 0. So it may be as simple as a no on the question, but they may ask us to rewrite this in that form with the function. F of x equals, what is the factor that we're dividing by, or the part we're dividing by? It's negative 4, so that turns into x plus 4. It's just going to change the sign there. And then we've got the red part here, x. What x do we start with? X to the 3rd minus 6x squared, 28x minus 110. And then we add our remainder, 435. There would be in that form. That form becomes more useful next week when we start doing more.
Okay. What about that k equals negative 4? Is that always give us what it wants us to divide by?
Yes, ma'am. Yeah. Yeah, they're going to give you what that k equals is what they want you to divide by. That's absolutely right. All right. Let's do another. f of x, so x to the fourth minus 2x cubed plus 4x squared plus 2x minus 5. We want to check k equals -1. -1 on the shelf. Roll it through synthetic. Multiply, add. Multiply, add. -1 is a 0. What's the part that goes in the first parenthesis there? X plus 1. Got 2 more examples, guys. We'll get out of here. All right. Let's say we had a function. Let's just use the same one again. And let's throw a fraction in there. We want to check k equals 1/2. Fractions are okay in synthetic division. They're not as nice to work with. They're kind of ugly to work with, but they're still doable. Okay. So when you do your synthetic division, everything's going to work the same. I'm going to give myself a little bit more room because I know I'm going to be writing some fractions. 1, -2, 4, 2, -5. Synthetic division works the same way, though. You're going to drop the first term down and multiply. And then you're just going to add. So -2 plus 1/2 would be -3/2. And then multiply. -3/4. And then 4 plus -3/4 would be 3 1/4, which would be 12, 13/4. And you can use a calculator to help you with these numbers here. It's 13/4 times 1/2 would be 13/8 plus 2 would be 16/8 plus 13. 16 plus 13 would be 29/8. Multiply that times 1/2. Obviously, we can tell that that's not going to be a 0. 29/16. Definitely not a 0. The remainder, let's see, 16 times 5 is 80. 80 minus 29 would be 51. -51/16. Again, you can use the calculator to help you do those. You go long enough without using one and making yourself do it right, you'll figure out how to not. You don't have to have one, but I don't see any reason you can't use one here. So this tells us that 1/2 is not a 0. We could still write it in that function notation if we wanted to. We needed to. It's not going to change anything about it. You still get, x minus 1/2, then it'd be x to the third minus 3 over 2 x squared, 13 over 4 x, 29 over 8, plus negative 51 over 16. Or you could just do minus 51 over 16. So fractions, legal to do synthetic division with. Okay. Fractions are legal to do that with. Also, legal to do synthetic division with. Let's take a function, x to the fourth minus 2x cubed plus 4x squared plus 2x minus 5, and let's throw a complex number in there. So far, the only way we've been able to encounter complex numbers is with square roots or the quadratic formula. Obviously, this is not a quadratic equation, but they're telling us check out 1 plus 2i. That's a zero of this. They're saying, is this a zero of that? So check it out. Now, here's the funky thing about it. Is if it is a zero, that doesn't mean it's an x-intercept. Because remember when we had the quadratics and it had complex solutions, they never crossed the x-axis. Complex, if this is a zero, it's a zero of it, but it doesn't mean it's an x-intercept because it's complex. Complex ones can be zeros, but not x-intercepts. If it's a real number, if it's a zero, it has to be an x-intercept. But that's not the case with complex. So I'll show you how easy this is. This is actually not that bad. It looks like it's just murderous, but it's not. Set up the same way. Only thing different that I might do is give yourself a little bit more room because you got complex number. They just take up more room. So I just stretch it out a little bit further. Same format. Drop the 1, multiply. But you're multiplying 1 times 1 plus 1 times 2i. And then when you add those together, you're adding negative 2 plus negative 1. Those are the real parts. So that'd be negative 1 plus 2i. And this is where I pick up the calculator to save myself a little bit of a time. Remember, your calculator can do complex numbers. That it can say 1 plus 2i times negative 1 plus 2i. And it can simplify it much quicker than you can. I'm not saying you can't do that with your brain. I'm just saying it makes it a little faster that turns into negative 5. It take me a little bit. I had to go negative 1 times 1, negative 1 times 2i is negative 2i. And then I had to say 2i times 1 is 2i. And then 2i times 2i would be 4i squared. And then I had to simplify that. So that takes a little time. So I use the tool you got in your hands and use that to help you simplify that faster. It ends up being negative 5 there. So 4 plus negative 5 is negative 1. And now that multiplication I can do pretty quickly. Negative 1 minus 2i. So that'd be 1 minus 2i. And then I've got to multiply that again. So I'm going to do 1 plus 2i. And I'm doing 1 minus 2i this time. I get positive 5. That works out really nice because now my remainder is 0. Okay, so that tells me that 1 plus 2i is a 0 of that polynomial. Now, here's the difference. You won't write that in the polynomial form with the parentheses and then the plus the remainder. You won't do that with the i's left in there. That ain't going to happen. Okay. Now, interesting fact that happens here that we'll touch on next week is if 1 plus 2i is a 0 of that polynomial, you get 1 minus 2i for free. That they come in complex conjugate pairs. That if 1 plus 2i is a 0, 1 minus 2i has to be a 0 as well. Right? That happens with the complex solutions to that. All right, I'm gonna write some problems down that you might want to look at to prep for your Canvas quiz. Page 305, 1 through 57 odd. Page 30, 89 through 94. And then the first section about circles, page 185, 1 through 12. There's not a whole lot on those. Okay, so you could look at those problems and get an idea of what to be prepared for as far as the Canvas quiz coming up. Okay.